Hello. Um, we are going to start a new chapter, chapter 8, about estimation. By the way, I flipped the left and right. Previously, my left was your right when you see the video, but now I realized I how to change it, and so it's much better because when I say like when I say something like small or large, then I try to flip my image, but it was very difficult. But now what I do is exactly what you see, so I feel more comfortable making some kind of making some direction with my hands. Anyhow, so chapter 8 is about estimation. So I guess I don't need to explain what it's going to be about. It's about estimation. But it takes a little bit. So estimation. When I say estimation, you have a good idea what I'm going to do. But as usual, I'm going to define the underlying structure, how we approach to the estimation problem statistically, and we'll think about what is a good estimation method, and what kind of criteria we can use to evaluate an estimator. Let's think about the first thing you have to understand is the difference between population and sample. So I have mentioned these two in chapter 1. So at that time, it was not that important at that time. But from now on, this is the most important concepts you have to distinguish. So first, population is the set of all objects of interest. So this is just everything. So for example, if you'd like to estimate the presidential election results, then the population is all likely voters in the election. All voters votes in the election. So population is our target. This is what we want to know. So estimation is basically as a process of knowing and like guessing something, and population is the target. So then there must be something different. So if you know the target, if you know the population, then you don't need any statistics. It's just computation. So if all the votes are counted the night after the election, then it's not anymore statistics. It's just sure thing. So everything is certain. There is no randomness. There is no uncertainty, and you know the results. So you know how many voters voted for this candidate and that candidate. So then, from then, there is no room for statistics at all. So obviously, in statistics, when I say the population, that means we do not know the population, and we cannot survey, we cannot observe all the elements in the population. That's an implicit assumption. Otherwise, we don't need statistics. And on the other hand, the sample is what we observe. So population is not observed, not fully observed, but some of the population, some part of the population is observed, and we call that a sample. So this is a simple diagram that illustrates the relationship. So literally I don't know how many voters are going to vote in this election, but anyhow, at this point, or like at this point, we cannot interview all the voters. We cannot observe all the votes. So, like for example, like a certain number of voters are surveyed, like 1,000, or depending on the fund available to the researcher. So that's still 1,000 is a large number, but still that is just a part of the population. Of course, as the sample size increases, your estimation will be more accurate. That's obvious because you know a larger part of the population, right? So that's the basic structure of statistical inference. So not only estimation, but in more general, that's statistical inference. And simply speaking, we would like to estimate the population using the sample, like based on the observation about the sample. And there are two different processes. The one is the random sampling. We learned what is the random sampling in chapter 7. Simply put, in our structure, from the population, we observe some sample. That is random sampling. You sample a certain number of observations from the population. So randomly choose some members of the population, and we call that a sample. And in chapter 7, we learned how the random sampling, what distribution random sampling generates, and we know it's always a normal distribution, so it's very nice. So now we understand this process. Random sampling generates a normal distribution, right? A sampling distribution is a normal distribution when the sample size is large enough. That was the result, the conclusion of chapter 7. And in the following chapters, we learned this process to understand the other way, to implement inference. So statistical inference is going the other way. Using the sample, we observe the sample, but we do not observe the population. So we would like to infer about the population using the sample. That is statistical inference. It's a process to make statements about the population using the sample. So, like in the presidential election example, what percentage of voters support candidate A or a certain candidate, and they will be the statistical inference methods will be discussed in chapters 8 through 10. So three chapters are devoted to statistical inference methods. Estimation is just one of them. The first part 1 is estimation, and as I said, we are going to heavily rely on the random sampling theory, because we only observe a part of the population, and so from a small part we have to guess the unobserved part. So to do that, we have to understand the relationship between the population and the sample, which was chapter 7, the central limit theorem. So if you have not finished watching chapter 7, then please go back and finish watching them. Otherwise, you will not be able to follow chapter 8 through 10. So it's very important to understand the random sampling process first. And then we are going to use the properties of the sampling distribution to evaluate and to define statistical inference methods. So please watch and just review chapter 7 if you are not familiar with the results. Okay. And another set of terms, parameter and sample. In chapter 5 and 6, when we learned binomial distribution and normal distribution, I used the term parameter in a different way. At that time, parameter meant just a small number of measures, numerical measures, that describes much more information, right? For example, binomial distribution is summarized by two parameters, n and p, and normal distribution is also summarized by two parameters, mean and variance, like that. So at that time, parameter meant more like something like summary without any loss of information. But now in this inference chapter, its meaning is a little bit different. Even though basically there is not a big difference, but we are going to use it in a different angle. So in this chapter, when I say parameter, it means any numerical measure about the population. If it is about the population, that is a parameter. So mean, median, variance, probability, whatever can be a parameter. So you can, simply speaking, parameter is exactly the number you are guessing. You want to estimate the mean, or I want to estimate the probability at 0, for example. So parameter is just any number you want to estimate. You are interested in, but it is unknown. So it should be unknown, but you are interested in. So this parameter is the target, and the sample is just the counterpart of parameter. So parameter is calculated from the population. It's about the population mean, population probability, but you can do the same thing from the sample. You can calculate the mean from the sample. You can calculate the probability from the sample. So so this is a typo. I think I'm going to stop this video here, and I'm going to fix the typo and restart this page in the next video. I'm sorry about the typo. But the typo is too crucial, too critical, so I have to fix it. So please continue in the next video.